So regarding that trigonal bipyramidal structure, we got some conclusions. Today let us observe some important examples on the basis of VSEPR theory. So this is trigonal bipyramidal structure. In the trigonal bipyramidal structure, 3 electron pairs are in one plane, and above that plane one electron pair, below that plane one more electron pair is there. Totally 5 electron pairs are available. In those 5 electron pairs, I mentioned here BE, this E stands for equatorial. So 3 equatorial pairs are available and 2 axial pairs are available. And in 2 sets of these equatorial and axial, normally these equatorial bonds are shorter than the axial bonds. And in this trigonal bipyramidal structure, they arrange with the position of lone pairs. In the last class, we concluded that in the trigonal bipyramidal structure, for getting minimum repulsions, అంటే ఎలక్ట్రాన్ జంటల మధ్య వికర్షణలు తక్కువ రావడానికి ఆ ఎలక్ట్రాన్ పేర్స్, ఆ లోన్ పేర్స్ ఎప్పుడు కూడా మనము ఈక్వటోరియల్లో ఉంచుకోవాలి. దాన్ని బేస్ చేసుకొని ఫస్ట్ లోన్ పేర్ and 2 lone pairs and 3 lone pairs. That means in trigonal bipyramidal structure, we got 3 possibilities. This one is called as a seesaw structure, and this one is called T-shape, and this one is called linear shape. This seesaw structure is also called as distorted tetrahedron and also called as folded square type. So in this trigonal bipyramidal structure, to get minimum repulsions, the first conclusion is the lone pairs we have to accommodate in the equatorial position. Next, if you observe these 3 examples, this is perfectly 5 equivalent bonds are available. So here no problem, all 5 chlorines are available. But in the second structure, different atoms are available, fluorine as well as chlorine. So in this trigonal bipyramidal structure, if you have different types of atoms, then most electronegative atom always we have to accommodate in the axial position. అంటే ఎక్కువ రుణ విద్యుదాత్మక కలిగినటువంటి మూలకాన్ని మనం యాక్సియల్లో అమర్చుకోవాల్సి వస్తూ ఉంటుంది. ఇక్కడ కూడా మనం చూసుకున్నట్లయితే PF3Cl2 molecule. In this PF3Cl2 molecule, 2 fluorines in the axial positions. Third fluorine among these 3, 1 position occupied by fluorine. So second conclusion is most electronegative atom you have to accommodate in the axial position in the trigonal bipyramidal structure. And one more example is XeO2F2 molecule. In this XeO2F2 molecule, we have double bonded oxygen. Then this double bonded oxygen always we have to accommodate in the equatorial position. అంటే కనుక ఆ అణువులో మనకి డబుల్ బాండ్స్ కనుక ఉన్నట్లయితే ఆ డబుల్ బాండ్స్ని మనం కంపల్సరీగా ఈక్వటోరియల్ పొజిషన్లో మనం ఉంచుకోవాలి. ఇప్పుడు మనం ఆక్టాహెడ్రల్ స్ట్రక్చర్ గురించి తెలుసుకుందాం. ఇన్ దిస్ ఆక్టాహెడ్రల్ స్ట్రక్చర్ టోటల్ 6 pairs are available. Here like this I arranged these 4 electron pairs. Here I arranged 4 electron pairs like this. If you observe both these 2 structures are identical structures. One is square plane above the plane and below the plane. That's why this structure is also called as square bipyramidal. So in this square bipyramidal structure or octahedral structure, what is the position of lone pairs? To explain that, observe these examples here. First, accommodation of first lone pair. I put that lone pair here. In the second structure, I put lone pair here. Don't say this is axial, this is equatorial. But if you observe these 2 structures, one square plane, that square plane above one lone pair is available, below one bond pair is available. ఇప్పుడు దీన్ని మనం స్క్వేర్ ప్లేన్గా తీసుకున్నట్లయితే అబవ్ లోన్ పేర్ ఉంది, బిలో బాండ్ పేర్ ఉంది. అంటే ఈ రెండు కూడా మనకి ఐడెంటికల్ స్ట్రక్చర్స్. ఇందాక మనకి ట్రైగోనల్ బైపిరమిడల్ స్ట్రక్చర్లో వాట్ వీ కంక్లూడెడ్, ద లోన్ పేర్ యూ హ్యావ్ టు అకామిడేట్ ఇన్ ద ఈక్వటోరియల్ పొజిషన్. ఆల్ 3 లోన్ పేర్స్ possibilities. One first lone pair, first equatorial position, second lone pair, second equatorial position, third lone pair in the third equatorial position. But in the case of octahedral structure, the lone pair, first lone pair, anywhere we can accommodate. అంటే ఆ ఫస్ట్ లోన్ పేర్ని ఈ ఆక్టాహెడ్రల్లో ఉన్నటువంటి ఈ 6 స్థానాల్లో మనం ఎక్కడైనా సరే అమర్చుకోవచ్చు. కాకపోతే ది అకామిడేషన్ ఆఫ్ సెకండ్ లోన్ పేర్, అంటే సెకండ్ ఎలక్ట్రాన్ పేర్ని, లోన్ పేర్ ఆఫ్ ఎలక్ట్రాన్స్ని ఎక్కడ మనం అరేంజ్మెంట్ చేసుకోవాలి. సో ఇక్కడ చూడండి, ఈ ఫస్ట్ స్ట్రక్చర్లో ఫస్ట్ లోన్ పేర్ ఆల్రెడీ ఇక్కడ ఉంది మనకి, సెకండ్ లోన్ పేర్ మనం ఇక్కడ అమర్చుకున్నాం. అదే ఈ స్ట్రక్చర్లో ఫస్ట్ లోన్ పేర్ ఇది, సెకండ్ లోన్ పేర్ ఇది. అంటే ఇప్పుడు ఈ లోన్ పేర్కి కనుక మధ్య మనం బాండ్ యాంగిల్ కనుక మనం చూసుకున్నట్లయితే, ద యాంగిల్ బిట్వీన్ దీస్ టూ లోన్ పేర్స్ ఇట్ ఈస్ 90 degrees. వెరాజ్ హియర్ బిట్వీన్ దీస్ టూ బాండ్ యాంగిల్ ఈస్ 180 degrees. అంటే ఇక్కడ మనకి 90 degree repulsions ఉన్నాయి, ఇక్కడేమో మనకి 180 degree repulsions ఉన్నాయి. దీన్ని బట్టి మనం ఏం చెప్పుకోవచ్చు, 90 degree repulsions ఎక్కువగా ఉంటాయి కాబట్టి ఎప్పుడు కూడా మనకి అరేంజ్మెంట్ ఆఫ్ ఎలక్ట్రాన్ పేర్స్ మనం గమనించినట్లయితే అందులో వికర్షణలు మనకి రిపల్షన్స్ మినిమం ఉండాలి, అప్పుడే దట్ మాలిక్యూల్ ఈజ్ మోర్ స్టేబుల్. సో దాన్ని బేస్ చేసుకొని this becomes incorrect representation of octahedral structure containing 2 lone pairs, and this is the correct representation of octahedral structure containing 2 lone pairs. So what is the conclusion? In the octahedral structure, first lone pair anywhere we can accommodate. What is the position of second lone pair? The position of second lone pair is exactly opposite to the first lone pair. Now coming to the octahedral structure containing multiple bonds. Definitely both multiple bonded compounds always opposite to each other like lone pairs. In the case of previous trigonal bipyramidal structure, the multiple bond always you have to accommodate in the equatorial position. But here first lone pair in octahedral structure, first lone pair at any position, second lone pair opposite to first lone pair. Next, accommodation of double bond, accommodation of first double bond anywhere. Then what about accommodation of second double bond exactly opposite to first double bonded structure. So very important conclusions in this trigonal bipyramidal structure and octahedral structure. Now based on that, if you observe on tabular form I am giving here, number of electron pairs, arrangement of electron pairs, molecular geometry and examples. So here number of electron pairs 2. If we have 2 electron pairs, that molecule is linear, I am representing like this. And if you have electron pairs 3, that molecule is trigonal planar. And if you have electron pairs 4, that molecule is tetrahedral. Similarly, if you have electron pairs 5, the structure is trigonal bipyramidal structure. Observe, this is called as trigonal plane, one above the plane, one below the plane. That's why this is called a trigonal bipyramidal structure. And here in 6 electron pairs, in the square plane, 4 pairs are there, one above the plane, one below the plane. That's why this octahedral structure is also called as square bipyramidal structure. 2 electron pairs, 3 electron pairs and 4 electron pairs, 5 electron pairs and 6 electron pairs. In these we don't have lone pairs. అంటే అన్నీ కూడా మనకి బంధ జంటలే తీసుకున్నాం, అందుకనే మనకి ఎటువంటి డీవియేషన్ కానీ డిస్టార్షన్ కానీ లేదు. అదే కనుక మనకి ఆ మాలిక్యూల్లో కనుక లోన్ పేర్స్ కనుక ఉన్నట్లయితే డెఫినెట్గా ఎలక్ట్రాన్ పేర్ జామెట్రీ ఒక రకంగా ఉంటుంది, మాలిక్యులర్ షేప్ ఒక రకంగా ఉంటుంది. సో దాన్ని ఇప్పుడు మనం చూసినట్లయితే నౌ అబ్జర్వ్ molecule type AB to E. This E stands for number of lone pairs and B stands for bond pairs. That means totally if you add number of bonding pairs and number of lone pairs, we are getting total electron pairs. So in this molecule we have total 3 electron pairs. Out of 3 electron pairs, previously if all 3 are bond pairs, then the structure is called as trigonal bipyramidal structure. In those 3 electron pairs, if one is lone pair and 2 bond pairs are there, observe here, arrangement of electron pairs is trigonal planar, but shape of the molecule is bent. So in the competitive examinations, carefully we have to observe whether they are asking electron pair geometry or molecular shape. So if they are asking electron pair geometry, both bonding pairs and lone pairs, both we have to count. If they asked molecular shape of the molecule, compulsory we have to consider bond pairs of electrons. So electron pair arrangement is trigonal planar, and shape of the molecule is, if you ignore this lone pair, then shape becomes bent. For this 2 examples are given. Now coming to molecular type AB3, means totally 4 pairs are there. Out of 4 pairs, 3 bond pairs and 1 lone pair. Then electron pair arrangement is tetrahedral, but to describe molecular shape, if you ignore this lone pair, it becomes a pyramidal structure, or we call it as a trigonal pyramidal structure. Previously we have trigonal planar, that is different. Now this is trigonal pyramidal shape. Suppose if you have like this all 3 orbitals, it is trigonal planar. If we have like this 3 electron pairs, then it is called as trigonal pyramidal structure, not bipyramidal, trigonal bipyramidal structure. One example is given. Now if you observe AB to E2 type, AB to E2 means 2 bond pairs and 2 lone pairs are there, means here also totally 4 electron pairs are available. Then electron pair geometry is tetrahedral, but to describe the molecular shape, if you ignore these lone pairs of electron, then shape of the molecule becomes bent. One example like H2O. In the next, we have AB4E type. AB4E means 4 bond pairs and 1 lone pair. So totally 5 electron pairs are there. Totally 5 electron pairs means the electron pair structure, electron pair arrangement is trigonal bipyramidal. But if you observe the molecular shape, if you remove this lone pair, then it becomes seesaw structure, or also called as distorted tetrahedron, or also called as folded square. But among these three, normally this AB4E type of molecule, we call it as a seesaw structure. Best example is SF4 molecule. Next, coming to AB3E2 type. AB3E2 means 3 bond pairs and 2 lone pairs, 3 bond pairs, 2 lone pairs, electron pair geometry is trigonal bipyramidal structure, and shape of the molecule becomes T shape. That means if you remove these lone pairs of electron, this becomes T shape. And example is ClF3. Next, AB2E3 type means 2 bond pairs and 3 lone pairs. So all 3 lone pairs occupies equatorial position. Then if you remove these lone pairs, then shape of the molecule becomes linear. Then what is the arrangement of electron pair geometry is trigonal bipyramidal. 2 examples I am giving here. One is I3 minus ion, triiodide ion. Another one is called XeF2. This I3 minus also called as polyhalide ion. Totally now we have 6 electron pairs, 5 bond pairs and 1 lone pair, and here 4 bond pairs and 2 lone pairs. Then first lone pair at any position, but the second lone pair is opposite to first lone pair. That's why this is AB5E, electron pair geometry is octahedral, but if you remove this lone pair, then it becomes square pyramid. Previously I told this octahedral is called as square bipyramidal structure, but one lone pair is available, that's why molecular shape becomes square pyramid. Now if you have 2 means 4 bond pairs and 2 lone pairs, then this becomes AB4E2 type. Electron pair arrangement is octahedral structure, but if you remove these 2 lone pairs, the molecule becomes square planar. The example is XeF4. So ఇప్పుడు నేను కొన్ని ఎగ్జాంపుల్స్ ఇస్తాను, అందులో ఎన్ని బాండ్ పేర్స్ ఉన్నాయి, ఎన్ని లోన్ పేర్స్ ఉన్నాయి అని మనం చూద్దాం. అది ఒక ఇంపార్టెంట్ స్టాండర్డ్ క్వశ్చన్ ఇన్ ఆల్ టైప్స్ ఆఫ్ కాంపిటేటివ్ ఎగ్జామినేషన్స్. Suppose I am giving here a molecule like SF4, sulfur tetrafluoride. In this, how many bond pairs and how many lone pairs are available near central atom? Then sulfur belongs to 6th year group, group 16. That sulfur contains 6 valence electrons. Next, fluorine, each electron of sulfur. Now I am taking 4 electrons of sulfur, and then we got 4 bonds here. Then this is called as bond pair, bond pair, bond pair, bond pair. Remaining 2 electrons is considered as lone pair. So overall, in this SF4 molecule, if you observe, total 1 lone pair is available and 4 bond pairs are available. So 1 lone pair, 4 bond pair means this is now called as AB4E type. If this is AB4E type SF4, then what the structure of this molecule means? Molecular shape of the molecule is seesaw structure, also called as distorted tetrahedron, or also called as folded square type, but popularly called as seesaw molecular structure, molecular shape for SF4. Now I am taking one more example. SO3, sulfur trioxide. So in this sulfur trioxide, near central atom sulfur, how many lone pairs are available? Let us verify. So sulfur, 6 valence electrons are available, 6th year group elements, and 3 oxygens are there. So 2 oxygens, and 3rd oxygen. That means because each oxygen valence is 2, each oxygen can form 2 bonds. That's why 2 electrons of sulfur I am utilizing for one oxygen atom. So, among these two, one is called sigma bond, one is called pi bond. That is why among sigma and pi bond, generally sigma bond describes the shape of the molecule. So, based on that I am ignoring pi bonds, but overall this molecule is called as 3 electron pairs are available, AB3 type. So, no lone pairs in SO3 molecule, that is why 0 lone pairs in SO3 molecule, then shape of this molecule becomes trigonal planar structure. Molecular shape is trigonal planar. Now, let us move to next example. Now, I am writing ICl4 minus ion. In this ICl4 minus ion, let us verify the central atom contains how many lone pairs of electrons. So, central atom is iodine, it is 7th A group element, it has totally 7 valence electrons and 4 chlorines we have, first chlorine, second chlorine, third chlorine, fourth chlorine. That means totally we got 4 bond pairs. Because of negative charge, I am writing one extra electron here. So, overall it becomes ion containing 2 lone pairs near central atom. So, overall this molecule is called as AB4E2 type molecule. Then according to VSEPR theory, if we have 4 bond pairs and 2 lone pairs near central atom, shape of this molecule is square planar. Molecular shape is square planar structure. Now, I am writing XCF2 molecule. In this XCF2 molecule, let us verify xenon contains how many lone pairs of electrons. Xenon 8th group, or it has 8 electrons in the valence shell. Out of 8 electrons, 2 electrons involved in bonding with 2 fluorine atoms, and there were out of 8 electrons, 2 electrons for fluorine. So, overall this molecule contains now 3 lone pairs and 2 bond pairs. Therefore, this molecule comes under AB3E2 type of molecule. Then according to VSEPR theory, molecule containing 3 bond pairs and 2 lone pairs, the molecular shape becomes linear structure. ఈ విధంగా మనం VSEPR థియరీని కనుక మనం చూసినట్లయితే, ఈ VSEPR థియరీ ప్రకారం మనకి అణువుల యొక్క ఆకృతుల్ని, అలాగే బంధకోణాల్లో వచ్చినటువంటి డీవియేషన్స్ కూడా మనం పరిశీలించుకోవచ్చు. కాకపోతే ఇప్పుడు మన అమోనియా మాలిక్యూల్ కనుక మనం తీసుకున్నట్లయితే, అమోనియా మాలిక్యూల్లో టోటల్గా మనకి 4 ఎలక్ట్రాన్ పేర్స్ ఉన్నాయి. అవుట్ ఆఫ్ దోస్ 4 ఎలక్ట్రాన్ పేర్స్ 3 are bond pairs and 1 is lone pair. Then according to VSEPR theory, total electron pairs 4, electron pair structure is tetrahedron, but because of lone pair, the molecular shape becomes pyramidal structure or trigonal pyramidal structure. So, experimentally the bond angle in ammonia is 107 degrees. If you have a regular geometry, suppose if you take CH4 methane molecule, in that 4 electron pairs here, that all those 4 electron pairs are bond pairs. Therefore, tetrahedral structure and bond angle is 109 degrees, exactly matched with experimental values. But in the case of ammonia, the bond angle becomes 107 degrees. Even though 4 electron pairs are there, bond angle becomes 107 degrees. That means now we have distortion in the bond angles. That distortion in the bond angle due to the presence of lone pairs of electrons. Yesterday in the last class, what we concluded, the presence of lone pairs causes some repulsions in the molecule. Because of the repulsions, some deviations in the bond angles were observing. Mainly ఆ లోన్ పేర్ అనేటువంటిది పూర్తిగా సెంట్రల్ ఆటమ్కి సంబంధించింది. అదే మనం బాండ్ పేర్ కనుక మనం తీసుకున్నట్లయితే, దట్ బాండ్ పేర్ బిలాంగ్స్ టు బోత్ ద ఆటమ్స్. దాన్ని బట్టి మనం చూసుకున్నట్లయితే ఆ లోన్ పేరు వెన్ కంపేర్డ్ టు బాండ్ పేర్, దట్ లోన్ పేర్ ఆక్యుపైస్ మోర్ స్పేస్ అరౌండ్ ద సెంట్రల్ ఆటమ్, అండ్ దేర్ బై we concluded that lone pair repulsions are more than lone pair bond pair repulsions, more than bond pair repulsions. So, based on that, in CH4 all are bond pairs, so bond pair repulsions minimum, So that's why no distortion in the bond angles. If we take ammonia molecule, one lone pair is available, 3 bond pairs are there. So in that we have lone pair bond pair as well as bond pair repulsions, but due to domination of lone pair bond pair repulsions, the bond angle decreases from 109 to 107. If you observe in the case of water molecule H2O, it contains total 4 electron pairs. Out of 4 electron pairs, 2 are lone pairs and 2 are bond pairs. That's when H2O we have lone pair repulsions, lone pair repulsions, and bond pair repulsions all are available, but due to domination of lone pair repulsions, the bond angle still decreases to 104 degrees. If you have one lone pair, 109 to 107. If you have 2 lone pairs, 109 to 104. So more decrease in the bond angle if you have more number of lone pairs. So best examples, these 3 basic examples: methane without lone pair, ammonia 1 lone pair, H2O containing 2 lone pairs under 4 electron pairs, under tetrahedral electron pair structures. సో ఈ విధంగా మనకి అణువుల్లో వచ్చినటువంటి ఈ డీవియేషన్స్ని ఇంకా ఎఫెక్టివ్గా ఎక్స్ప్లెయిన్ చేసుకోవడానికి తర్వాత ఇంకొక సిద్ధాంతాన్ని వాళ్ళు ఇంట్రడ్యూస్ చేయడం జరిగింది. ఇప్పుడు లెట్ us మూవ్ టు డిస్కస్ థరోలీ అబౌట్ ది నెక్స్ట్ థియరీ టు డిస్క్రైబ్ ది డీవియేషన్స్ అండ్ స్ట్రక్చర్స్, డీవియేషన్స్ ఇన్ ద బాండ్ యాంగిల్స్ అండ్ ఎలక్ట్రాన్ పేర్ స్ట్రక్చర్స్, మాలిక్యులర్ షేప్స్ అండ్ సమ్ ఎక్స్ట్రా ఎగ్జాంపుల్స్ ఆల్సో లెట్ us. సో ఇప్పుడు మనం టు డిస్క్రైబ్ ది bond angles and molecular shapes, let us move to one more concept called as hybridization. So what is the meaning of this hybridization? Hybridization means the process of intermixing of atomic orbitals present in the valency shell and thereby forming a new set of orbitals called as hybrid orbitals. అంటే ఈ వ్యాలెన్సీ షెల్లో ఉన్నటువంటి ఆర్బిటాల్స్ ఒకదానితో పాటు కలిసిపోయి అవి ఒక న్యూ ఆర్బిటాల్స్ని ఏర్పాటు చేసుకొని ఆ న్యూ ఆర్బిటాల్స్ని ఉపయోగించుకొని వాళ్ళు దే ఎక్స్ప్లెయిన్ అబౌట్ ది బాండింగ్ ఇన్ ద మాలిక్యూల్స్. సో దిస్ టైప్ ఆఫ్ ప్రాసెస్ ఆఫ్ ఇంటర్మిక్సింగ్ ఆఫ్ అటామిక్ ఆర్బిటాల్స్ present in the valency shell of central atom is called as hybridization, and the new orbitals what we are getting is called as hybrid orbital. Now the definition given here: the process of intermixing of the orbitals of slightly different energies so as to redistribute their energies, resulting in the formation of new set of orbitals of equivalent energies and shape. అంటే ఈ వ్యాలెన్సీ షెల్లో ఉన్నటువంటి స్లైట్లీ డిఫరెన్స్ ఎనర్జీ ఉన్నటువంటి ఆర్బిటాల్స్ ఒకదానితో పాటు కలిసిపోయి అవి మళ్ళీ వాటి యొక్క ఎనర్జీని రీడిస్ట్రిబ్యూట్ చేసుకొని తద్వారా ఒక కొత్త ఆర్బిటాల్ని ఏర్పాటు చేసుకుంటాయి, హ్యావింగ్ ఈక్వలెంట్ ఎనర్జీస్ అండ్ షేప్. అంటే మనకి ఏర్పడినటువంటి న్యూ ఆర్బిటాల్స్కి సేమ్ ఎనర్జీ ఉంటుంది, వాటి షేప్స్ కూడా ఐడెంటికల్గా ఉంటాయి. సో ఇటువంటి ప్రాసెస్ని మనం హైబ్రిడైజేషన్ అని చెప్పేసి అంటూ ఉంటాం. సో ఈ హైబ్రిడైజేషన్లో ఇప్పుడు మనం వాటిలో దాని యొక్క ఇంపార్టెంట్ సైలెంట్ ఫీచర్స్ ఏంటో మేము చూద్దాం. హియర్ ఇన్ దిస్ hybridization, the first one is the number of hybrid orbitals is always equal to the number of the atomic orbitals that get hybridized. అంటే ఎన్ని అటామిక్ ఆర్బిటాల్స్ అయితే హైబ్రిడైజ్ అవుతాయో అన్నే మనకి హైబ్రిడ్ ఆర్బిటల్స్ అనేవి వస్తూ ఉంటాయి. ఫర్ ఎగ్జాంపుల్, ఒక ఎస్ ఆర్బిటాల్ ఒక పి ఆర్బిటాల్ హైబ్రిడైజ్ అయినట్లయితే అప్పుడు మనకు వచ్చేటువంటి హైబ్రిడ్ ఆర్బిటల్స్ ఎన్ని అంటే 2 వస్తాయి. సో ద మిక్సింగ్ ఆఫ్ 1s and 1 p orbitals leads to the formation of 2 hybrid orbitals. So that is the first point. Next, if you observe these hybrid orbitals form most effective bonds when compared to the atomic orbitals, because in the case of this covalent bond formation, the most important point is the strength of the bonds. The strength of the bond depends upon the extent of overlapping of orbitals. That extent of overlapping of orbitals depends upon the directional character of the orbital. అంటే ఒక ఆర్బిటాల్ కనుక డైరెక్షనల్ క్యారెక్టర్ ఎక్కువగా కనుక ఉన్నట్లయితే అది ఏర్పాటు చేసేటువంటి బాండ్ కొంచెం స్ట్రాంగ్గా ఉంటుంది. సో వెన్ కంపేర్డ్ టు ప్యూర్ అటామిక్ ఆర్బిటాల్స్, దీస్ హైబ్రిడ్ ఆర్బిటాల్స్ హ్యావ్ సమ్ మోర్ డైరెక్షనల్ క్యారెక్టర్. That's why these hybrid orbitals they can form effective bonds when compared to the normal atomic orbitals. That's when second point is given, that the hybrid orbitals are more effective in forming stable bonds than the pure atomic orbitals. Next, so ఎప్పుడైతే మనకి ఈ హైబ్రిడ్ ఆర్బిటాల్స్ వస్తూ ఉంటాయో ఈ హైబ్రిడ్ ఆర్బిటాల్స్ వెంటనే స్పేస్లో కొంత పొజిషన్ ఆక్యుపై చేస్తూ ఉంటాయి. సో ఏ విధంగా ఉంటాయంటే సెంట్రల్ ఆటమ్ చుట్టూతో కూడా అవి ఎప్పుడూ కూడా వాటి మధ్య రిపల్షన్స్ మినిమం అయ్యేటట్లు అరేంజ్మెంట్ అయి ఉంటాయి. సో the hybrid orbitals symmetrically arranged around the nucleus so that the repulsion between them will be minimum. This is a very important point related to stability of the molecules. And the electron pairs or the hybrid orbitals always occupy some space around the nucleus of central atom. What type of space they occupy means such that they acquire minimum repulsions. If they acquire minimum repulsions, automatically they acquire maximum stability. Next one is regarding this hybridization. Normally, what type of orbitals involved in hybridization means not all atomic orbitals, only the orbitals present in the valency shell only participate in hybridization. అంటే బాహ్య స్థాయిలో ఉన్నటువంటి అటామిక్ ఆర్బిటాల్స్ మాత్రమే హైబ్రిడైజేషన్ ఇన్వాల్వ్ అవుతాయి. The orbitals present in the valency shell of the atom are hybridized. ఇంకో ముఖ్యమైన విషయం ఏంటంటే ఇక్కడ మనకి ఆ ఎలక్ట్రానిక్ కాన్ఫిగరేషన్ కనుక మనం చూసినట్లయితే వ్యాలెన్సీ షెల్లో మనకి హాఫ్ ఫీల్డ్ ఆర్బిటాల్స్ ఉంటాయి. అంటే సపోజ్ ఎస్ ఆర్బిటాల్ కనుక మనం తీసుకున్నట్లయితే ఒక ఎలక్ట్రాన్ ఉండొచ్చు. అదే కొన్ని సందర్భాల్లో ఎస్ ఆర్బిటాల్లో 2 ఎలక్ట్రాన్స్ ఉంటాయి. అప్పుడు ఎటువంటి ఆర్బిటాల్స్ మనకి హైబ్రిడైజేషన్లో ఇన్వాల్వ్ అవుతాయి అంటే హాఫ్ ఫీల్డ్ ఆర్బిటాల్స్తో పాటు కంప్లీట్లీ ఫిల్ అయినటువంటి ఆర్బిటాల్స్ కూడా ఒక్కోసారి పార్టిసిపేషన్ అవుతూ ఉంటాయి హైబ్రిడైజేషన్లో. అందుకనే ఇట్ ఈస్ నాట్ నెసరీ దట్ ఓన్లీ half filled orbitals participate in hybridization. In some cases, even filled orbitals of valency shell take part in hybridization. Next, ఇంకో ముఖ్యమైన విషయం ఏంటంటే ఒక ఆటంలో ఉన్నటువంటి ఆర్బిటాల్స్ వేరే ఆటంలో ఉన్నటువంటి ఆర్బిటాల్తో హైబ్రిడైజ్ అవ్వవు. అంటే ఒక ఆటంలో ఉన్నటువంటి వాలెన్సీ షెల్లో ఏవైతే ఆర్బిటాల్స్ ఉంటాయో అవి మాత్రమే హైబ్రిడైజేషన్ ఇన్వాల్వ్ అవుతాయి. ఇస్ గివెన్ హియర్. The atomic orbitals of only one atom can participate in hybridization. Next, if you observe in the beginning postulate, I told that these hybrid orbitals, they form most effective bonds when compared, most stable bonds when compared to pure atomic orbitals. And in addition to that, one more conclusion is these hybrid orbitals always form sigma bonds. But in the case of pure atomic orbitals, they can form sigma bonds as well as pi bonds. సో ఈ హైబ్రిడైజేషన్లో మనం ముఖ్యంగా మనం గమనించుకోవాల్సింది ఏంటంటే ఈ హైబ్రిడైజేషన్ ఎన్ని ఆర్బిటాల్స్ అయితే ఇన్వాల్వ్ అవుతాయో అన్నే మనకి హైబ్రిడ్ ఆర్బిటాల్స్ ఫామ్ అవుతూ ఉంటాయి. ఈ హైబ్రిడ్ ఆర్బిటాల్స్ ఫామ్ అవ్వాలి అంటే వ్యాలెన్సీ షెల్లో ఉన్నటువంటి ఆర్బిటాల్స్ మాత్రమే హైబ్రిడైజేషన్లో పార్టిసిపేట్ అవుతాయి. ఇంకో ముఖ్యమైన విషయం ఏంటంటే ఒక ఆటంలో ఉన్నటువంటి ఆర్బిటాల్స్ వేరే ఆటంలో ఉన్న ఆర్బిటాల్స్తో హైబ్రిడైజేషన్ అవ్వవు. ఒక ఆటంలో ఉన్నటువంటి వ్యాలెన్సీ షెల్లో ఉన్న ఆర్బిటాల్స్ మాత్రమే హైబ్రిడైజేషన్ ఇన్వాల్వ్ అవుతూ ఉంటాయి. సో ఈ హైబ్రిడైజేషన్ అయిన తర్వాత వచ్చినటువంటి హైబ్రిడ్ ఆర్బిటాల్స్ ఆ న్యూక్లియస్ చుట్టూతా కూడా ఎలా అరేంజ్మెంట్ అయి ఉంటాయంటే వాటి మధ్య వికర్షణలు అనేటువంటివి తక్కువ వచ్చేటట్లు అరేంజ్మెంట్ అవుతూ ఉంటాయి. అంటే ఆల్ దీస్ ఎలక్ట్రాన్ పేర్స్ ఆక్యుపైస్ అరౌండ్ ద న్యూక్లియస్ ఆఫ్ సెంట్రల్ ఆటమ్ సచ్ దట్ between those electron pairs we required minimum repulsions and thereby we are getting maximum stability. Now if you observe after observing these silent features of hybridization, now I am giving some important types of hybridizations. Some important types, so many are there. One is sp hybridization, sp2, sp3, sp3d, sp3d2 and sp3d3. If you move to coordination compounds, in coordination compounds we have variety of hybridizations. So here in chemical bonding chapter mainly we are concentrating these 6 hybridizations: sp, sp2, sp3, sp3d, sp3d2 and sp3dt. What is the meaning of sp hybridization? One s orbital and one p orbital mixed together and produces 2 hybrid orbitals. Each hybrid orbital is called as now sp hybrid orbitals. So in sp hybridization we are getting 2 sp hybrid orbitals. What is the meaning of sp2 hybridization? Mixing of one s orbital and 2 p orbitals and thereby forming 3 sp2 hybrid orbitals. Like that, intermixing of one s orbital and 3 p orbitals leads to 4 sp3 hybrid orbitals, and 1 s, 3 p and 1 d gives 5 hybrid orbitals, here 6 hybrid orbitals, here 7 hybrid orbitals. So sp, sp2, sp3 and sp3d, sp3d2 and sp3d, and depending on this we are getting shapes for the molecule also. In the silent features of hybridization we have an important conclusion, one important point is there. After the hybridization, the hybrid orbitals occupy some space around the nucleus such that between those electron pairs, we are getting minimum repulsions. For example, I am taking sp hybridization. In sp hybridization, we are getting two sp hybrid orbitals. What is the position of those two sp hybrid orbitals? With 45-degree bond angle or 90-degree bond angle or 180-degree bond angle. అంటే ఆ రెండు sp హైబ్రిడ్ ఆర్బిటాల్స్ ఏ విధంగా అరేంజ్మెంట్ ఉంటాయి అంటే వాటి మధ్య మినిమం రిపల్షన్స్ రావాలి. మినిమం రిపల్షన్స్ రావాలి అంటే ఆ రెండు హైబ్రిడ్ ఆర్బిటాల్స్కి మనకు మ్యాక్సిమం సపరేషన్ అనేది ఉండాలి. మ్యాక్సిమం సపరేషన్ అంటే కంపల్సరీగా 180 డిగ్రీస్ తీసుకుంటాం. కాబట్టి ఆ sp హైబ్రిడైజేషన్లో ఇన్వాల్వ్ అయినట్లయితే ఆ సెంట్రల్ ఆటమ్ మనం sp హైబ్రిడైజేషన్కి ఇన్వాల్వ్ అయితే ఆ మాలిక్యూల్కి లీనియర్ స్ట్రక్చర్ అనేది వస్తూ ఉంటుంది విత్ ఏ బాండ్ యాంగిల్ ఆఫ్ 180 డిగ్రీస్. అదేవిధంగా మనం sp2 హైబ్రిడైజేషన్ తీసుకున్నట్లయితే ఇన్ దిస్ sp2 హైబ్రిడైజేషన్ వీఆర్ గెటింగ్ 3 sp2 హైబ్రిడ్ ఆర్బిటాల్స్. మరి ఆ 3 sp2 హైబ్రిడ్ ఆర్బిటాల్స్ ఏ విధంగా అరేంజ్మెంట్ అయి ఉంటాయి స్పేస్లో అంటే వన్స్ అగైన్ బిట్వీన్ దోస్ 3 sp2 హైబ్రిడ్ ఆర్బిటాల్స్ వీ రిక్వైర్డ్ మినిమం రిపల్షన్స్. మినిమం రిపల్షన్స్ రావాలి అంటే sp2 హైబ్రిడైజేషన్లో ఏర్పడినటువంటి ఆ 3 sp2 హైబ్రిడ్ ఆర్బిటాల్స్ కంపల్సరీగా 120 డిగ్రీస్తో సపరేషన్ అయి ఉండాలి. అప్పుడే ఆ మూడింటికి రిపల్షన్స్ అనేవి మినిమం ఉంటాయి. అందుకని sp2 హైబ్రిడైజేషన్ ఉన్నట్లయితే ఆ మాలిక్యూలు మనం 120 డిగ్రీ బాండ్ యాంగిల్ మాలిక్యూల్ అని చెప్పి చెప్తూ ఉంటాం. ఆ విధంగా డిఫరెంట్ బాండ్ యాంగిల్స్ ఆల్సో వీ హ్యావ్. లెట్ us మూవ్ టు సమ్ మోర్ పాయింట్స్ రిలేటెడ్ టు దిస్ హైబ్రిడైజేషన్. నెక్స్ట్ I am giving few examples I am giving here. First one is sp hybridization. What is the meaning of sp hybridization? Intermixing of one s and one p orbital and thereby forming two sp hybrid orbitals. So one s orbital is taken, one p orbital is taken, then we got two sp hybrid orbitals. This is an example given here, beryllium. So these are the two sp hybrid orbitals of beryllium. Now these two sp hybrid orbitals of beryllium overlap with the p orbital of chlorine. Here I mentioned here pz. That means I am taking z axis as internuclear axis or molecular axis. That means in this BeCl2 molecule we are getting two bonds here. What type of bonds? One is sp orbital of beryllium overlap with p orbital of chlorine. So this is called as spp overlapping, and this is also called as spp overlapping. So overall in BeCl2 molecule, in beryllium dichloride or beryllium chloride molecule, we have two BeCl bonds and both are sigma bonds. Both are formed by what type of overlapping? spp overlapping. So this is called as nature of bonding. So this also we have to practice. So in BeCl2, what is the nature of bonding? Nature of bonding means what type of orbitals participate in bonding, what type of orbitals participate in overlapping. So sp hybrid orbital of beryllium overlap with the p orbital of chlorine. So because of this sp hybridization, just now we concluded that these two sp hybrid orbitals, to acquire minimum repulsions, we need 180 degree separation, and thereby the molecule, overall molecule becomes linear. Suppose if they ask what is the molecular shape of BeCl2, then we have to say it is a linear molecule. Now let us move to sp2 hybridization. In this sp2 hybridization, the process of intermixing of one s and two p orbitals. So the black one is s orbital and the blue one is p orbital. That's why the s orbital and the two p orbitals mixed together and produces three sp2 hybrid orbitals. To get minimum repulsions, those three, we required 120 degree separation, and therefore that those three orbitals becomes planar. Now these are called sp2 hybrids. sp2 hybrid orbitals 3 we are getting. Now I am taking here one example, BeCl3. So in BeCl3, the central boron atom, if you observe, its electronic configuration is 2s2 2p1 ground state. Excited state configuration is 2s1 2p2. So 2s1 2p2. So now one s orbital and two p orbitals mixed together and produces three sp2 hybrid orbitals. Now these three sp2 hybrid orbitals separately overlap with chlorine atoms, three chlorine atoms. Once again, chlorine contains p orbital. So sp2p, sp2p, sp2p. That means in BeCl3 molecule, what is the nature of bonding means? We are getting three boron chlorine sigma bonds. These sigma bonds are formed by overlapping of sp2 orbital of boron with p orbital of chlorine, and therefore suppose if they ask what is the molecular shape of BCl3, then we have to say it is a trigonal planar structure with a bond angle of 120 degrees. Now let us move to one more example, that is sp3 hybridization. So in this sp3 hybridization, intermixing of 1s and 3p orbitals and thereby forming 4 sp3 hybrid orbitals. Here if you observe, 1 s orbital and 3 p orbitals mixed together and produces 4 sp3 hybrid orbitals. Then according to hybridization, in sp3 hybridization, all those 4 sp3 hybrid orbitals acquires minimum repulsion with this separation, that is 109.5 degrees. So this is called as tetrahedral bond angle, 109.5 degrees. So for this, one example is given here, CH4 methane formation. So in this methane formation, if you observe carbon electronic configuration, ground state is 2s2 2p2 and excited state configuration is 2s1 2p3. Now it has 4 orbitals with 1 electron. Now 1s orbital, 3 p orbitals, then we are getting sp3 hybridization, then we are getting 4 sp3 hybrid orbitals. Now each sp3 hybrid orbital overlap with here s orbital of hydrogen. That's why this bond is called sp3s bond. Like that we have in methane molecule 4 equivalent identical bonds. This is a big difficulty in the case of valency bond theory. According to valency bond theory, pure orbitals participate in bonding. Pure orbitals are overlapped. That means according to valency bond theory, s orbital of carbon overlap with s orbital of hydrogen. That is called SS bond. And 3 p orbitals separately overlap with 3 s orbitals of 3 hydrogen atoms, and thereby we are getting 3 sp bonds. That means in the methane formation, according to valency bond theory, we are getting some uncertainty regarding shape, regarding bond angles and regarding overlappings also, because we have 1 SS bond and 3 sp bonds. So clearly it indicates SS bond is normally weaker than sp bond. That means in methane molecule, according to valency bond theory, all bonds are not equivalent. So to overcome that difficulty, but experimentally it is concluded that in methane all 4 bonds are equivalent. Then this theory successfully explained that part. In valency bond theory, 1 SS and 3 sp bonds, but according to hybridization theory, 4 bonds are there, but here all 4 bonds are equivalent. That's why in the formation of methane under sp3 hybridization, it contains 4 CH sigma bonds. Those sigma bonds are formed by sp3 orbital of carbon with s orbital of hydrogen. So 4 equivalent bonds are there. So this is a good example for sp3 hybridization. Now let us move to one more example. Now I am taking ammonia. In this ammonia formation, sp3 hybridized nitrogen. So this nitrogen, if you observe its electronic configuration, it is 2s2 2p3. In this electronic configuration, one orbital contains paired electrons. Then according to hybridization theory, we have an important conclusion. It's not necessarily always only half filled orbitals participate in hybridization. In some cases, completely filled orbital also can take part in the hybridization. For that, this example is given here. In ammonia formation, nitrogen undergoes sp3 hybridization. Then we are getting 4 sp3 hybrid orbitals. Here, hybridization is only for orbitals, not for electrons. That means there is no change in the distribution of electrons. Before hybridization, one orbital contains paired. Then after hybridization, one hybrid orbital contains a pair of electrons. So before hybridization, after hybridization, no change in the number of hybrid orbitals, number of orbitals also. That's why before hybridization, one atomic orbital contains paired electron. Then after hybridization, one sp3 orbital contains paired electrons. Now this is called sp3 hybrid orbital lone pair. Now this blue color sp3 hybrid orbital of nitrogen now overlap with s orbital of hydrogen. So sp3s. That means in the case of ammonia molecule, total 4 pairs are there. Out of 4, one is lone pair, remaining 3 are bond pairs, and those bonds are formed by sp3 and s overlapping. This lone pair totally belongs to central atom. That's why this lone pair occupies more space around the central atom. If it occupies more space around the central atom, then these 3 come closer for minimizing the repulsions. Because bond pair repulsions are less, when compared to lone pair bond pair repulsions. When these three come closer, definitely the bond angle decreases. That's why according to 4 electron pairs, normally we are expecting 109-degree bond angles, but in the case of ammonia, the bond angle is reduced to 107 degrees due to the presence of lone pair bond pair repulsions. Now let us move to one more example under this hybridization. H2O molecule is given. Here also sp3 hybridized oxygen, that means central oxygen atom undergoes sp3 hybridization. It gives 4 sp3 hybrid orbitals. Out of 4 sp3 hybrid orbitals, if you observe its electronic configuration, it is 2s2, 2p4, means that oxygen contains total 6 electrons. Out of 6 electrons, 2 orbitals are paired and 2 orbitals are half-filled. That's why after hybridization also, 2 hybrid orbitals contain paired electrons and 2 hybrid orbitals are half-filled. Those half-filled orbitals only overlap with s orbital of hydrogen, and thereby in H2O molecule, 2 lone pairs and 2 bond pairs are there. Because lone pair, just now I concluded that lone pair occupies more space around the nucleus of central atom, so it occupies more space. This lone pair also occupies more space, then these 2 bond pairs come closer, and therefore bond angle further decreases. That's why in the case of H2O, bond angle becomes 104 degrees. So the presence of lone pairs definitely causes some distortion in the bond angles. But in some cases, the effect of lone pairs also can, even though lone pairs are there, lone pair effect is cancelled. We will discuss later on such type of examples also. Normally, if you take CH4, ammonia and H2O molecule, CH4 4 bond pairs, ammonia 3 bond pairs and 1 lone pair, H2O 2 bond pairs and 2 lone pairs. So as number of lone pairs increases, the bond angles decreases. In methane 109, in ammonia 107, in H2O 104 degrees. There are the some conclusions related to ammonia and H2O molecule. Now let us move to one more example. Ethylene molecule, C2H4, also called as ethene. This is the best example for carbon having sp2 hybridization. So in C2H4 molecule, 2 carbons are available. So each carbon undergoes sp2 hybridization. If each carbon undergoes sp2 hybridization, near each carbon we are getting 3 sp2 hybrid orbitals and 3 sp2 hybrid orbitals. Overall, in ethylene molecule, near both carbons we are getting 6 sp2 hybrid orbitals. Out of 6 sp2 hybrid orbitals, here this overlapping is sp2 orbital of carbon overlap with sp2 orbital of another carbon atom. This is called sigma bond, sp2 sigma bond. And this sp2 orbital overlap with s orbital of hydrogen. This is called sp2s. This is also sp2s. This is also sp2s. This is also sp2s. That means in the carbon in the excited state, its configuration is 2s1, 2p3. So in this formation of C2H4, this carbon uses sp2 hybridization. Now what about this orbital? This orbital is called as unhybridized orbital. So that orbital is p orbital. So that p orbital, now I mentioned here, this is unhybridized p orbital, this is also unhybridized p orbital. Now between carbon-carbon, sigma bond is available, and carbon linked with hydrogen, sigma bond. So that's why now we got, according to the first A diagram, we got here total 5 bonds. All 5 bonds are sigma bonds. Now all these are in the one plane. Then what is the position of this p orbital? Perpendicular to that plane. So if it is perpendicular to that plane, there is no chance of sigma bond formation. Then 2p orbital of one carbon atom laterally overlap with 2p orbital of another carbon atom and form sigma bond. So that sigma bond present perpendicular to the molecular plane, above and below the CC sigma bond. So that diagram I am representing in C structure here. So this is sigma bond, sigma bond, sigma bond, 5 sigma bonds are available. This is pi electron cloud present above and below the sigma bond. So overall, in this ethylene molecule, if you observe how many bonds are there means, or what type of bonds first, nature of bonding. So in this ethylene molecule or ethene molecule, now I am writing here 1 CC sigma bonds and 4 CH sigma bonds and 1 CC pi bonds. So total 6 bonds are there. The CC sigma bond formed by sp2 overlapping, the CH sigma bond formed by sp2s overlapping, CC pi bond formed by pp overlapping. This is called nature of bonding. Now, in this particular formation of ethylene molecule, now I am asking how many hybrid orbitals are available and how many atomic orbitals are available. They are asking the ratio between number of hybrid orbitals and atomic orbitals. If you observe first diagram, sp2, 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 sp2. So, total 6 hybrid orbitals we have. Now, coming to atomic orbitals, s orbitals, 4 s orbitals we have. So, in the sigma bond formation, sp2 orbitals 6 are there. Out of 6, one sp2 overlap with another sp2 orbital of carbon atom here. This is sp2 sp2 overlapping. Both are hybrid orbitals. Here one is hybrid orbital, another one is atomic orbital. That means according to first structure, without considering pi bonds, 6 hybrid orbitals are available and 4 atomic orbitals are available. Now, coming to the pi bond formation, pi bond is formed by lateral overlapping of p orbitals. So, that is why these p orbitals also atomic orbitals. So, if they asked number of hybrid orbitals, so H I am writing here 6 hybrid orbitals are available. Now, I am asking here how many atomic orbitals we have. Normally, in the examination, they are ignoring these p orbitals. They are counting only s orbitals as atomic orbitals. P orbitals also unhybridized orbitals only. Those are also called as atomic orbitals. So, these 2 p orbitals also we have to count. So, 4 s orbitals and 2 p orbitals. That means atomic orbitals also 6. If they ask ratio between hybrid orbitals and atomic orbitals, it becomes 1:1. So, carefully we have to draw the structure and then we have to verify what type of hybrid orbitals are there, how many hybrid orbitals are available. Along with that, we have to verify what type of atomic orbitals we are using and how many types of, how many types also. This is s orbital, this is p orbital. So, all those unhybridized orbitals or atomic orbitals also we have to count if they ask ratio between hybrid orbitals and atomic orbitals. Now, let us move to one more example. Before going to that example, just now we concluded that the formation of sigma bonds and pi bond present above and below the sigma bond plane. So, this is planar, this is CH2 and CH2, all are present in one plane. In that we have sigma bond, CC sigma bond and CH sigma bonds also. And this p orbital present above and below the plane. This blue shade is above the plane and this one is below the plane. So, this overlapping above and below the plane. So, that is why this gray, this colored other than blue colored, it is called as pi electron cloud. So, this is called as molecular plane CH2 CH2. Then what is the position of that pi bond? That pi bond present above and below the molecular plane. So, this also you have to concentrate. Now, if you observe one more example, acetylene molecule under sp hybridized carbons, C2H2, IUPAC name is ethine. Then this carbon electronic configuration excited state 2s1 2p3. Now, carbon sp hybridization, these two are called unhybrid orbitals, unhybridized orbitals. Now, if carbon undergoes sp hybridization, it gives 2 sp hybrid orbitals. Second carbon also gives 2 sp hybrid orbitals. So, overall we are getting 4 sp hybrid orbitals. Out of 4 sp hybrid orbitals, sp orbital of one carbon atom overlap with sp orbital of another carbon atom linearly and form sigma bond. Remaining sp hybrid orbitals overlap with 1s orbital of hydrogen. This is sigma bonds in the formation of C2H2. How many sigma bonds are available here? 1 sigma bond and 2 sigma bond. Total is 3 sigma bonds are there. But 1 sigma bond formed by sp-sp overlapping and remaining 2 sigma bonds formed by sp and s overlapping. Now, because carbon we are using only sp hybridization, near each carbon we have 2 unhybridized orbitals, both are p orbitals. Now, those two I am showing like this, and these two are perpendicular to each other. In addition to that, these two perpendicular to this plane also. That is why, suppose I mentioned here 2px orbital, 2px orbital. then the 2px orbital overlap with 2px orbital only, because it is a very important point. What type of orbitals can participate in overlapping means the direction in which the orbitals are concentrated, those same type of directional character orbitals only can participate in overlapping. That's why if I mention 2px with 2py is a wrong overlapping. 2py orbital overlap with 2py and 2px with 2px. So overall, by using one unhybridized orbital, we are getting one pi bond. By using another unhybridized orbital, we are getting second pi bond. So in this acetylene molecule or ethane molecule with C2H2 molecular structure, between carbon and carbon, now we have one sigma bond that is formed by sp-sp overlapping. Next we have two more pi bonds are there. Those pi bonds are formed by overlapping of pure p orbitals in between carbons. Now each carbon bonded to one hydrogen. So thereby carbon, carbon, triple bond and each carbon bonded to hydrogen. So sigma bonds 3 and pi bonds, 2 pi bonds we have. And this is the representation of acetylene molecule. sp-sp overlapping, sp-s overlapping, the blue one is sp-sp overlapping, and 2 pi bonds I mentioned here. These 2 pi bonds perpendicular to each other and those two perpendicular to the sigma bond plane also. So overall in this acetylene molecule, how many sigma bonds and how many pi bonds means 3 sigma and 2 pi bonds. Once again I am asking here, what is the ratio between hybrid orbitals and atomic orbitals? So if you count hybrid orbitals, 1, 2, 3, 4 hybrid orbitals are there. Atomic orbitals, s orbital and 2 p orbitals here, 2 p orbitals here. Totally 6 atomic orbitals are there. Previously in the case of ethylene, both have same number. But in the case of acetylene, 4 hybrid orbitals and 6 atomic orbitals. So this is about formation of acetylene under sp hybridization of carbon involving d orbitals in hybridization. First one is formation of PCl5. So first let us conclude phosphorus can form PCl5 or not. Suppose I am asking one more question here, same type of molecule also formed by nitrogen or not. Among NCl5 and PCl5, which one exists? Now I am taking nitrogen. Its configuration is 2s2 2p3, 2s2 2p3. Now I am taking phosphorus. Its configuration is 3s2 3p3. It contains 3d orbitals also. So due to the presence of empty 3d orbitals, definitely phosphorus can form more than 4 bonds. That means this pair, దీన్ని మనం ఎగ్జైట్ చేసినట్లయితే ఒక ఎలక్ట్రాన్ d ఆర్బిటాల్లోకి వెళ్ళిపోయి మొత్తం మనకి 5 అన్పేర్డ్ ఎలక్ట్రాన్స్ వస్తాయి. It can form PCl5. But if you observe nitrogen, due to lack of empty d orbitals or empty orbitals in the valency shell, no chance of excitation. That's why nitrogen normally form 3 bonds. It can form 4th bond also, but more than 4 not possible. That's why in the case of nitrogen, the maximum covalency is 4 due to lack of empty orbitals in its valency shell. But in the case of phosphorus, due to the availability of empty d orbital in its valency shell, it can form more than 4 bonds also. That's why one example is given, that is PCl5. So in this PCl5, now I am writing here P star configuration, excited configuration. It becomes 3s1, 3p3 and 3d1. Now we have totally 1 s orbital, 3 p orbitals and 1 d orbitals. That means 5 atomic orbitals are there. Those 5 atomic orbitals intermixed together and produces 5 sp3d hybrid orbitals. Those 5 sp3d hybrid orbitals overlap with 5 chlorine atoms differently and becomes total 5 electron pairs are there. All electron pairs are bond pairs. If all electron pairs are bond pairs, then we have trigonal bipyramidal structure, and these 3 chlorines are called as equatorial chlorines, and these 2 chlorines are called axial chlorines, and equatorial bonds are shorter than axial bonds. That's why if this PCl5 molecule is heated, it gives 2 species. One is PCl3, another one is Cl2. What type of Cl2 it is? That Cl2 is axial chlorines, slightly weaker than these bonds. So this is the example for sp3d hybridization. So if you observe sulfur electronic configuration, that is 3s2, 3p4, 3d0. So in the ground state, it contains only 2 half-filled orbitals. So normally we are expecting 2 covalent bonds here, but in the molecular structure we have SF6, 6 bonds we required. To get 6 bonds we required 6 unpaired electrons. That is why excitation takes place. Excitation, one more excitation. So this is called first excited state and this is called second excited state. So the structure of SF6 explained in the second excited state of sulfur. So that electronic configuration is 3s1, 3p3, 3d2. So 3s1, 3p3 and 3d2. Now sp3d2 hybridization. Now we are getting 6 sp3d2 hybrid orbitals. Then all those 6 hybrid orbitals, to acquire minimum repulsions, they arrange in this structure, octahedral structure, also called as square bipyramidal structure, square plane, one above the plane and one below the plane, square bipyramidal structure or octahedral structure. Here all electrons are participate in bonding, no lone pairs are there, regular geometry, octahedral structure, and we are getting SF6 molecule. Now after observing all these examples, let us summarize all these points. If you observe this tabular form, total electron pairs, number of bond pairs, number of lone pairs, shape of molecules or ions, next hybridization. Now 2 electron pairs I am giving here and both are bond pairs, then it is called as sp hybridized and linear molecule or ion. Similarly 3 electron pairs are there, all 3 are bond pairs, then this is called trigonal planar structure, and 2 bond pairs and 1 lone pair, bent structure. This is shape of molecules, not electron pair structure. For this total electron pair structure is trigonal planar. But if I asked shape of molecules or ions or molecular shape or ion shape, then we have to ignore lone pairs, then we have to consider bond pairs. That is why 3-0 trigonal planar, 2-1 becomes bent. For both, hybridization is sp2. Now I am taking 4 electron pairs, 3 possibilities I am giving here. This is 4-0, AB4